Ever since I was a kid, one question has never quite let go of me. After the wow signal, after Planet 9, it's still here, quietly waiting. How far could we ever actually go? This is the farthest we have ever reached. Voyager, a small, patient machine drifting past the edge of everything we call home. It looked back once and took this. Everything you have ever known, everyone who ever lived, is that single pale blue dot. We have always wanted to leave. We built towers of fire just to lift ourselves a little way off the ground. The universe is generous with beauty and merciless with distance. This is the fastest thing we have ever made. Even it, at over 400,000 miles an hour, has only brushed the edge of our own star. And yet we can see so far. Point a telescope at an empty patch of sky, wait, and thousands of galaxies quietly appear. The newest eyes go further still, back toward the first light, to galaxies that were old before the Earth began. Everything out here is drifting away from us, quietly, all the time. This is home, our galaxy, roughly 100,000 light-years of stars we will almost certainly never cross. And this is our nearest large neighbor, Andromeda, 2.5 million light-years away, and still one of the closest things to us. A century ago, one man told us the rule that changes everything. Nothing travels faster than light. And another looked deeper and noticed something stranger still. The galaxies weren't just sitting there, they were rushing apart, and the farther away they were, the faster they fled. And some lights, I think, we will only ever watch, never reach. Look as far as it is possible to look, and you arrive here. The oldest light there is, the wall at the edge of the visible. Tonight, new observatories open their eyes, mapping more of that sky than anyone ever has. We watch and we listen, reaching outward with everything we have. But here is the quiet, unsettling truth. The space between us and everything else is still growing, and slowly, the reachable universe is shrinking. So let's begin at the edge of what we can still touch, and follow it outward, as far as it goes. Right now, one of our machines is already out there, further than anyone has ever been, still moving, still faithfully calling home. It has been traveling for almost 50 years, and it is only just beginning to leave us behind. Its voice now takes almost a full day to reach us. A signal, crawling at the speed of light for 23 hours. And still, it has barely stepped outside the front door. Past Neptune, the sunlight thins, and the familiar planets give way to a colder, quieter country. Out here drift the frozen worlds we have only just met: Pluto, Eris, and further still, lonely Sedna. Beauty does not stop at the edge of the map, but the sun's true family reaches much further. A vast, faint shell of ice we call the Oort cloud. Our fastest traveler will not even reach its inner edge for another 300 years. And to pass all the way through it, to truly leave the sun behind, would take something like 30,000 years. Only then would the next star begin to feel close. Proxima Centauri, the nearest star to our own, lies just over 4 light-years away. It sounds almost near. It is not. If our fastest spacecraft were even aimed at it, the journey would take roughly 70,000 years. That is longer than our entire recorded history, several times over. This is the wall we keep arriving at. Not a lack of will, but the simple, brutal size of the gap. Because there is a speed limit built into the universe itself. Light crosses the whole distance from the sun to the Earth in about 8 minutes. Nothing we know of moves faster, and next to it, we are almost standing still. Our quickest machines travel at a tiny fraction of 1% of that speed. So the galaxy, for now, remains something we can mostly only look at. 100 billion stars, turning slowly, almost all of which we will never so much as approach. And our galaxy is only one, among perhaps 2 trillion others. The more we learn to see, the larger the silence around us seems to grow. And here is the part that took me a long time to sit with. The distances themselves are not fixed. They are still growing. It took us a long time to notice because the change is far too slow to ever watch happen. The first clue was hidden inside the color of the light itself. When something moves away from us, its light is stretched, shifted toward the red. In 1912, an astronomer named Vesto Slipher measured that stretch for the very first time. Oddly, the first galaxy he studied was moving toward us, not away. But almost every other one he measured was fleeing. For a while, no one quite knew what to make of it. Then, in 1927, a Belgian priest named Georges Lemaitre followed the mathematics to a startling place. The universe, he realized, did not have to be still. It could be growing. His paper, buried in an obscure journal, was almost entirely ignored. 2 years later, Edwin Hubble made the pattern impossible to deny. The farther away a galaxy sat, the faster it was rushing from us. And this is the strange heart of it. The galaxies are not flying through space. Space itself is stretching and quietly carrying them along with it. Picture a scattering of dots on the surface of something slowly inflating. Every dot sees all the others drift away, and not one of them is the center. Rewind that expansion far enough, and everything is drawn back together, back to a single, unimaginably hot beginning, about 13.8 billion years ago. Close to home, though, gravity still wins. Andromeda, our nearest large neighbor, is not fleeing at all. It is drifting toward us. Our small family of galaxies is bound together, and it will stay that way. It is only on the very largest scales that the expansion truly takes over. The great web of galaxies is slowly, endlessly pulling apart, and the light reaching us from the farthest of them left, long before there was an Earth to receive it. For most of a century, we were certain of just one thing about all this expansion, that it had to be slowing down. For most of a century, we assumed gravity would eventually slow the expansion down. It should have. All that matter, quietly pulling back on everything else. So in the 1990s, 2 teams set out to measure exactly how fast it was slowing. They tracked distant exploding stars, supernovae, as cosmic mile markers stretching back through time. For a moment, the measurements simply refused to make sense. And in 1998, they found the exact opposite of what everyone had expected. The expansion was not slowing at all. It was speeding up. Something was pushing the whole universe apart, faster and faster with every passing age. We still do not really know what it is. We simply call it dark energy. It is, quite literally, the defining feature of our universe, and it remains a mystery. It makes up around 68% of everything that exists, and ordinary matter, the stars, the planets, you and me, is barely 5% of it. The rest is hidden from us in ways we are only beginning to grasp. Unseen matter and this stranger force, together driving the acceleration onward. And acceleration changes everything about how far we could ever hope to go. A universe that merely expands, you could, in principle, still chase across. But a universe that accelerates pulls its most distant parts away faster than any light could cross. It is one of the strangest facts I have ever had to sit with, not because anything moves faster than light, but because space itself keeps stretching between us. And that quietly draws a line around us, a horizon we can never cross. Beyond that line lies most of the universe we can see, but can never touch. Right now, that boundary sits about 16 billion light-years away. It is almost too large a thought to hold in the mind at once. Everything past it is already lost to us, forever, no matter what we do. Of all the galaxies we can see, we could ever actually reach only a few percent. The rest, we will only ever watch. And that horizon is not fixed. Slowly, quietly, it is closing in. It is a difficult thing to feel, a loss on a scale we were never built to sense. One by one, the most distant galaxies are already crossing beyond it. Their light stretches, dims, and slowly reddens its way toward the invisible. Every year that passes, more of them slip quietly away. There is a strange, quiet grief in watching a thing you can do nothing to stop. In 100 billion years, the sky beyond our own galaxies will simply have gone dark. The evidence of the wider universe, the other galaxies, the expansion itself, will be gone. A civilization born into that far future would look out and see only their own island of stars. It would be their whole universe, and they would have no reason to imagine anything more. They would have no way, none at all, to know the rest had ever existed. In a strange way, we are the lucky ones, looking out now, while the evidence is still here to see. For now, at least, the sky above us is still full. Closer to home, though, our own small neighborhood will hold together. Bound by gravity, our small family of galaxies will stay near one another as the rest recedes. In fact, Andromeda and our own Milky Way are already falling toward each other. In a few billion years, they will merge into a single, vast, new galaxy. That merged island of stars will drift on, alone, across an ever-emptying sea. So how far can we really go? The honest answer is smaller than we would like it to be. A few worlds, perhaps, maybe one distant day, a single nearby star. The rest, we reach only with our eyes and with our questions. And I find I can live with that. Because maybe it is enough simply to have seen it at all. To have been here, looking outward, while the light of everything was still on its way to us. But we are not, I think, the kind of species that simply accepts a closed door. Even now, one of our machines is still out there, still moving quietly outward. In about 40,000 years, it will drift within a couple of light years of another star. It will be long dead by then, silent, carrying only a golden record of who we were. It is our first, faint attempt to cross the gap. To truly go, though, our rockets are hopelessly slow. They must burn fuel simply to carry more fuel, a losing bargain with distance. Even our fastest probe moves at a tiny fraction of what we would need. So for decades, people have dreamed of something far bolder. The dream of the stars has never really let us go. In the 1950s, physicists imagined riding nuclear explosions themselves. A great ship would drop bombs behind a heavy plate and surf the blasts. In theory, it might reach a nearby star within a single human century. But the idea was set aside when the world agreed to stop testing bombs in the sky. Still, the dreaming did not stop. A gentler dream needs no fuel at all, the solar sail. A mirror-thin sheet, pushed by nothing but the faint pressure of light itself. Slow at first, but endlessly patient, never once stopping its acceleration. And then the boldest idea of them all. In 2016, a project imagined probes no heavier than a paperclip. A vast bank of lasers on Earth would push them to a fifth of the speed of light. Fast enough to reach the nearest star in about 20 years, not 70,000. It is a beautiful, almost impossible thing to imagine. But at that speed, a single grain of dust would strike like a bomb. And how would something so tiny ever slow down or call home across the light years? For now, that dream too has quietly stalled. Every plan we make collides with the same immovable wall, the sheer size of the gap. And yet, the dreaming still does not stop. Because suppose, somehow, that we could go. Where would we even point ourselves? For most of history, we did not even know if other worlds existed at all. Now we know of more than 6,000 of them beyond our own sun. They are scattered through the galaxy, far more common than we ever dared to guess. We find them by watching for the faint, regular dimming as a world crosses its star. Some are giants, some are scorched, and a few are small worlds in the gentle zone, where a world might be neither too hot nor too cold for liquid water. And the very nearest one is astonishingly close to home. Proxima b, discovered in 2016, orbits our nearest star of all. Just over 4 light-years away, in the habitable zone, perhaps holding water. But its sun is a red dwarf, restless and prone to violent flares. Its atmosphere, if it ever had one, may have been stripped away long ago. We simply do not know yet whether it is a haven or a ruin. Further out, 40 light-years away, waits a stranger prize. TRAPPIST-1, 7 Earth-sized worlds circling one small, dim, red star. Up to 4 of them orbit where liquid water could just survive. From the surface of one, the others would hang huge and close in the sky. We do not yet know whether any of them truly live. Worlds we can see clearly now, and still cannot begin to reach. It is a strange comfort and a strange ache to have neighbors we can name but never visit. For now, they belong to our telescopes and not to our ships. So the oldest question returns, sharper than before. Not whether the wonders are real, but whether we can ever reach them. Even if we chose a target and built a ship, the journey would swallow lifetimes whole. No one who first stepped aboard would ever live to see the far shore. A world in miniature, then, sailing quietly onward for centuries. Children would be born in that moving dark, who never once knew the Earth. Grandchildren would arrive at a star their ancestors had only ever dreamed of. It asks something almost beyond us, to begin a journey we ourselves will never finish. To plant, in effect, a tree whose shade we will never once sit beneath. And a ship is a fragile thing to trust with 1,000 years of silence. One failure, one long unanswered silence, and that entire small world simply ends. So perhaps the truth is gentler and stranger than a ship full of people. Perhaps it will not be us who go at all, but the patient machines we send ahead. Small, patient, tireless, able to cross the centuries without ever growing old. It is a humbler kind of reaching, and perhaps a wiser one. They may reach those far shores and send back a single, quiet image. A world lit by another sun, seen at last with instruments of our own making. And maybe that is the true shape of it. We reach outward, not so much with our bodies, as with our endless curiosity, the way we always have, with questions thrown farther than we ourselves can ever follow. Every telescope, every probe, every faint signal is a hand extended into the dark. Not to grasp and not to hold, only to touch, however briefly. And there is something almost sacred in reaching for a thing you know you cannot keep. Because the wanting itself is a kind of arrival. To have looked up at all and wondered and quietly tried. The universe may be closing its far doors, slowly, across billions of years. But the near doors are still wide open. The moon, Mars, the quiet moons of the giants. There is a whole solar system, in fact, already within our actual reach. Worlds we could genuinely stand upon within a single human lifetime, if we only chose to. Maybe that is where the real answer lives. Not in the impossible distances, but the possible ones, close enough to touch, if we are patient and kind to ourselves, and a little lucky. As for the rest, the far galaxies, the vanishing light, we will love them the way we love anything at all that we cannot keep, fully and completely, and from a great and gentle distance. So, in the end, how far can we go? Farther, I think, than we fear, and never quite as far as we dream. Somewhere in between lies a real journey, waiting for someone brave enough to begin it. Whoever they are, and wherever they are bound, I hope they look back, just once, at the small blue world that wondered first. And these nearby worlds are stranger and lovelier than we often remember. Titan, a moon wrapped in thick orange haze, with rivers and lakes of liquid methane. Worlds so close that a message home would take only hours, not years. Europa, a moon of cracked white ice, laced with rust-brown fractures across its shell. And beneath that ice, a hidden ocean, larger than all the seas of Earth combined. It is one of the best places we know of to go looking for life beyond the Earth. Enceladus, smaller still, flinging bright fountains of water ice into space from its south. Each of these is a genuine frontier, sitting quietly within our own sun's family. Not light years away, but months, or a few short years, of real travel. A lifetime, spent well, is more than enough to reach any one of them. And standing on one of those distant moons, we would look outward again and wonder, exactly as we always have, about the farther shores we still cannot reach. For now, though, we keep looking outward and reaching and asking. We have spoken of distance across space, but there is another distance, just as vast and far stranger: time. The universe, for all its age, is astonishingly young. Barely 14 billion years have passed since the very first light. And the great age of stars has only just begun. A star like our own sun burns steadily for about 10 billion years. Ours is roughly halfway through its long, patient life. But it will not shine forever. In about 5 billion years, it will swell into an enormous, bloated red giant. It will swallow Mercury, then Venus, and scorch the Earth to bare, dry rock. It is a slow, certain fate, and there is a strange beauty in it. Then, almost gently, it will breathe its outer layers away into a glowing shell of gas, and what remains will collapse into a white dwarf, an ember the size of the Earth, impossibly dense, cooling slowly in the dark. That is the quiet death of an ordinary star. The very greatest stars, though, die far more violently. They burn through their fuel in only a few million years, living fast and bright. And they end in a supernova, a single star, for a few weeks, outshining an entire galaxy. From that violence come the seeds of everything. The iron in your blood, the calcium in your bones, was forged in the heart of a dying star. But it is the smallest stars, the humble red dwarfs, that are the true survivors. They burn so slowly, so frugally, that they can last for trillions of years. Long after our own sun is a cold, dark cinder, they will still be quietly glowing. The very last stars of all will be red dwarfs, fading out one by one some 100 trillion years from now. And when the final red dwarf gutters out, the long age of starlight will be over. What follows is a darkness we have no honest name for. The galaxies will no longer shine. They will only smolder with the dying embers of dead stars. White dwarfs cooling slowly to black. Neutron stars, silent and still. And the black holes. Over spans of time that break the mind, the galaxies themselves will slowly come undone. Their dead stars flung out into the dark, or swallowed by the giants at their hearts. And then, perhaps, even matter itself will begin to dissolve. The protons at the heart of every atom may not, in the very end, last forever. Slowly, across a length of time that makes a mockery of every word we have, they may simply decay away, until at last, only the black holes remain, vast, dark, and patient, drifting through an all but empty cosmos. And here is the strangest truth of all: even they do not last. Black holes are not quite eternal. Very, very slowly, they evaporate, bleeding away their mass, one faint particle of light at a time, into the surrounding dark. A star-sized black hole would take a number of years with 67 zeros just to fade away. The largest, the supermassive giants, far longer still. A 1 followed by 100 zeros. Numbers so vast that the very word long simply falls apart against them. And at the very end of that unthinkable wait, a black hole does not fade quietly. It finishes in a final, sudden flash, a last burst of light thrown into the dark. one by one, across eternities, the last black holes will wink out, each a tiny final spark in a rising ocean of darkness. And then, nothing. No stars, no galaxies, no matter, only cold and space and a silence with no end. This is what they call the Dark Era, the final, endless age of the universe. A cosmos still expanding, growing colder and emptier with every passing eternity. Everything that could ever happen has happened. Every fire has finally burned out. There is nothing left to change, and so, in a sense, nothing left for time itself to measure. It is the quietest ending imaginable. Not a bang, but an endless, gentle fading. And, I will be honest, it is a hard thing to hold in the heart. To even try to write these numbers down is to lose all sense of them entirely. A single trillion years is already far longer than the whole history of the universe so far, and the age of black holes stretches vastly, vastly beyond even that. Numbers with dozens of zeros, then hundreds, then more zeros than there are atoms in your body. If you tried to count just the zeros, one each second, your whole life would end long before you finished. This is not a distance you could ever walk, or fly, or even truly imagine. It is a depth of time so complete that the universe itself forgets it was ever young. And through all of it, the universe simply keeps expanding, patient and indifferent. It is almost too much to feel, and so most of the time we simply do not. And still, all of that lies impossibly, mercifully far ahead of us. But here is the thought that steadies me every single time. Those numbers, the trillions, the eternities, are so vast that they turn the whole picture around. Because it means that we are not, in fact, living anywhere near the end of things. We are living almost impossibly close to the very beginning. The universe is barely 14 billion years old, a single bright morning in a life of countless eternities. The stars are still burning, the galaxies are still turning, and still bright. The night sky above you is still full of light, light that will, one distant day, be gone. We did not arrive too late. We arrived astonishingly, wonderfully early. In the brief, luminous dawn of absolutely everything. And that, I think, quietly changes the meaning of the whole question. Because how far can we go was never only ever about distance. It was always quietly about time as well. How far can we go? Across space, yes, but also across the ages. And the honest answer holds both a sorrow and a grace. The far reaches, the distant galaxies, the deep future we will never truly touch. They will drift beyond us in space and long outlast us in time. But the near reaches are ours, and they are not small. A whole solar system to explore, a handful of nearby stars to dream toward, and billions of years of starlight still left to live beneath. That is not a consolation prize. That is a vast and shining inheritance. We are here, now, in the one brief window when the whole universe is full of light, when the sky still burns, and the questions still have answers we can actually chase. Every generation that has ever looked up has stood in this same rare morning, and wondered the same wordless thing. How far can we go? Farther than any single life. Never quite as far as the whole of the sky, but far enough to matter. Far enough to be worth every mile of the reaching. And maybe the going was never really the whole point. Maybe it was the looking, the wondering, the stubborn refusal to ever stop asking. The universe will have its long, cold, magnificent ending. But not tonight. And not for a length of time so vast it may as well be forever. Tonight, the stars are still here. So are we. And so is the wondering. So look up while the looking is still good. Let the distances be vast. Let the questions stay wide open. There is no hurry. There is so much time. More time and more sky than a single heart can ever hold. For now, rest easy. The sky will still be here tomorrow, and so, I hope, will you. Earlier I told you that light itself is the great limit, that nothing at all can cross the emptiness between the stars any faster. And that is entirely true. But I left out the strangest, most wonderful part of the whole story. Because the very same physics that seems to trap us here also hides, quietly, a most unexpected loophole. It is a loophole so strange that when it was first written down, even its own author could scarcely believe it. It comes, once again, from Einstein, and it is far harder to truly accept than any simple speed limit. He told us that time itself is not fixed, that it does not flow at the same rate for everyone, everywhere. The faster you move through space, the more slowly, from your own point of view, you move onward through time. It sounds like something lifted straight out of a poem, but it is plain, measured, and endlessly tested fact. We have proven it again and again, flying delicate atomic clocks aboard fast aircraft and orbiting satellites high above the Earth. A clock that travels quickly always returns having ticked a little less than the patient twin it left behind. At the everyday speeds we know, the effect is almost nothing at all. But approach the speed of light, and it becomes truly vast. Picture two twins. One stays quietly at home on the Earth. The other flies away, close to the speed of light, and comes back. The traveler steps down from the ship still young, barely aged at all by the long, swift voyage out and home again, and finds their twin grown old and gray, or gone entirely, whole generations already turned quietly to dust. They both lived through the very same journey. They simply did not live through the same amount of time. And this one strange, proven fact quietly changes everything about how far a single human life might actually reach. Suppose we built a ship that could accelerate gently and endlessly at exactly the familiar pull of Earth's own gravity. You would feel entirely normal aboard it, your feet pressed to the floor as it quietly gathered speed without any end. Within a year or two, you would already be racing along at a serious fraction of the speed of light itself. And your own time, without you ever once feeling it, would begin gently, steadily, quietly to slow. To the nearest star, a little over 4 light years away, you would arrive in only about 3.5 years of your own life. To the great glowing heart of our galaxy, some 28,000 light years off, you would step out onto that dazzling shore after only about 20 years of your own lived time. Though back on the Earth you left behind, 28,000 long years would already have quietly passed. Across the entire width of the Milky Way, 100,000 light years from one edge to the other. Perhaps only 25 years at most would ever pass for you aboard the ship. And to Andromeda, our great galactic neighbor, some 2.5 million light years away, a mere 28 years spent quietly sitting there inside your traveling ship, while 2.5 million years unspooled, entirely unseen, in the whole world behind you. In a single human lifetime, in principle, one determined traveler could cross the whole of the visible universe. The stars, it turns out, are not truly beyond our reach after all, not for the one who chooses to go. Only and always for the clock that stays behind. It seems at first like a pure and simple miracle, a great door thrown suddenly wide open onto the entire cosmos. But every door that swings suddenly open must, at the very same moment, close something else quietly behind it. And this particular door closes the single heaviest thing that there is. And that heaviest thing is simply this. While you fly, the entire universe outside your ship races on ahead of you. And the journey itself would look like almost nothing any human eye has ever once seen. As you climbed toward the speed of light, the stars ahead of you would begin, strangely, to crowd together. Sliding steadily forward, bunching and gathering into a brilliant, tightening ring of light directly in your path. Behind you, meanwhile, the sky would empty and darken, the stars all fleeing away into a deep, spreading black. And their very colors would change, a strange gift and a strange warning of just how fast you had come. The crowded stars ahead would shift toward a fierce blue, then a deep violet, then climb clean out of sight. Their light climbing quietly past anything at all that a human eye was ever built to hold. Behind you, what few stars still remained would redden and dim, and one by one, quietly wink out. You would fly then straight through a narrowing tunnel of blue-white fire into a rising wall of pure blackness. A view that not one single ancestor of ours ever once imagined. Beautiful and lonely and utterly, utterly strange. And yet, through all of it, your own small, quiet cabin would remain perfectly calm and perfectly still. A warm cup of tea resting untroubled on the table, while the entire universe rearranged itself just outside the glass. That is the strange truth of near-light travel. Not violence at all, but a vast, silent, endless, sliding strangeness. And a small clock on the cabin wall, ticking softly on, slower than any clock in all the wide world you had left. Out there, the entire sky would be squeezed and compressed into that one single, blazing eye of light ahead. Everything you were rushing toward, gathered and concentrated into one brilliant, unbearable point. Everything you were leaving behind, swallowed whole and silent by the deepening dark at your back. It is, perhaps, quite simply the loneliest view in all of physics. And also, I have always thought, one of the very most quietly and strangely beautiful. A single traveler and a single point of light, and the whole rest of creation held at bay on either side. It is the closest thing to true magic that the plain, honest laws of the universe will ever allow us. And it waits there, patiently, folded quietly inside the same physics that once seemed only to fence us in. You might cross all the way to a distant star in only a small handful of your own quiet years. But when you finally slow and turn to look back, the world you left has aged by whole centuries, or by eons. The people you loved will be long gone, their children's children gone. Even your language perhaps forgotten. To reach out across the sheer vastness of space, you must give up, entirely and forever, the time you came from. It is a door that swings open only one way. You may go outward always, but you can never truly go home again. Home will still be there, of course, waiting, but it will no longer be, in any way, the home that you once knew. And that, I think, is the real and honest shape of the answer we have been quietly circling all along. We truly can reach the stars. The physics itself genuinely allows it. The door really is standing open for us. But only by becoming a certain kind of one-way traveler, someone who trades their entire world for a far horizon, someone who steps forward into the deep future itself and lets everything familiar quietly fall away behind them. It would take a strange and rare and very brave kind of heart to ever willingly make that particular trade. To wave a last goodbye, not merely to a beloved place, but to an entire age of the whole turning world. And yet, I feel quite certain that there would always be at least a few who would still choose to go. There always have been such people. The ones who once sailed straight past the very edge of every known map, who left behind everything warm and safe and certain for nothing at all but the deep pull of the great unknown. Perhaps one distant day, some of us will finally do exactly that, out among the stars themselves, carrying just a little of the earth outward with them, a memory, a song, a single name, into a future they will never see, and leaving the rest of us behind, standing here to look up into the night and quietly wonder how far they got. And so the physics itself leaves us with a quiet, double-edged gift, held out in a single open hand. The whole universe is, in a strange and perfectly technical sense, within a single lifetime's reach, but only for the one who actually goes, and only if they are willing to let their own world go with it. Most of us, I suspect, would quietly choose to stay, to keep the faces we love close and grow old beside them. And there is nothing small or timid in that choice at all. It is simply its own quieter kind of courage, to love a place and a time and a handful of people fully, while knowing the whole vast sky is out there. Perhaps the deepest reach of all was never really about crossing the distance at all. Perhaps it was about learning to hold two things at once, the wonder of the far and the warmth of the near. To let the stars stay exactly as distant as they truly are, and to love them quietly anyway. Not as places we are somehow bound to conquer, but as a country we have only just begun, very gently, to map. Because here is what all of it, in the very end, seems to come quietly down to. The universe is not a wall built to keep us out. It never was, and it never will be. It is simply very, very large, and we, for our part, are still very, very new to it. We have only been looking up and truly wondering in this way for a few short thousand years. A single blink of an eye set against those long ages of stars we spoke of a while before. Give us just a little more time, a few thousand years more, a few million, and who knows how far we will have gone. The story of how far we can go is not remotely finished. In truth, it has barely begun. And you and I are here for the very start of it, for the first faint opening chapter. When the questions are all still enormous, and the answers are all still ours to chase. So let the distances stay as vast as they like. Let the stars keep their secrets a little while longer. There is time. There is so very much time. More of it, truly, than we could ever hope to spend. And there is a whole sky above you tonight, patient and glittering and quietly waiting, full of far places we may never once reach, and a few, perhaps, that we one distant day still will. For now, though, it is more than enough simply to lie here beneath it all, and to look, and to wonder, and to rest. We have spent so long asking how far we can go. But behind that lies a stranger, older question entirely. How do we even know, in the first place, how far away any of them truly are? You cannot stretch a measuring tape across the void. You cannot walk it off, or send a ruler to a star. For almost all of human history, the honest answer was simply that we did not know at all. A star might be near, or unimaginably far. A faint one might be close and dim, or blazing and impossibly distant. And so, patiently, over centuries, we had to invent an entire ladder just to climb out toward them. The very first rung of that ladder is a trick you can do right now, with nothing but your own two eyes. Hold up a finger and close one eye, then the other. It jumps against the far wall behind it. The nearer a thing is, the more it seems to shift. And the sky, it turns out, plays exactly the same game. As the Earth swings around the sun, the very nearest stars appear to shift, ever so slightly, against the distant ones. Measure that tiny shift, and a little careful geometry hands you the true distance to the star. In 1838, a careful German astronomer named Friedrich Bessel did it, for the very first time. He measured the faint shift of a modest star called 61 Cygni, and found it about 10 light-years away. It was the first moment in all of human history that we knew, truly knew, the real distance to another star. A single rung, climbed at last, the first honest measurement of the gulf between ourselves and the stars. But parallax has a hard limit. Push out far enough, and the little shift grows too tiny for any instrument to catch. For the deeper distances, we needed a second rung, and it came, quietly, from a woman the world had overlooked, Her name was Henrietta Leavitt, and she worked at Harvard among a group of women known simply as the computers. They were paid a few cents an hour to measure and catalog stars, by hand, from thousands of glass photographic plates. Leavitt studied a certain kind of restless star, a Cepheid, that slowly, rhythmically brightens and then dims again. And in 1912, from those quiet plates, she noticed something that would remake the entire universe. The slower a Cepheid pulses, she found, the brighter, in truth, it actually burns. It sounds so small. It was, in fact, a cosmic measuring rod, a way to read a star's true brightness from its beat. Here is why that one small discovery mattered so much. If two Cepheids pulse at the very same slow rhythm, they burn with the very same true brightness. So you find one of these stars, and you simply time it, patiently, night after night, as it swells and fades and swells again. Its rhythm quietly tells you how brightly it truly shines. Not how bright it merely looks from here, but how bright it actually is. And the gap between those two, its true glow and its faint appearance in the telescope, that gap is nothing less than distance. A candle you know should be blazing, yet which appears as the faintest ember, must simply be very, very far away. For the first time, we held a lantern we could carry out into the dark and read the distance straight off its flame. And here is the wonder of it. A Cepheid pulses the same way whether it sits nearby or deep inside some faraway smudge of light. Find one of these pulsing stars anywhere at all, and Leavitt's quiet law will tell you how far away it truly lies. Parallax had carried us out a few hundred light years. This carried us into the millions. It was a second rung, set high above the first, reaching into distances the old geometry could never hope to touch. The whole vast scale of the heavens suddenly lay open. If only someone would take up her ruler and go looking. But it is worth pausing here on the woman herself, because the world was slow and unkind in how it thanked her. Henrietta Leavitt did her work in near silence. An illness in her 20s had taken most of her hearing and never gave it back. She was one of the Harvard computers, a room of gifted women hired to do the patient, painstaking arithmetic of the stars. They were paid less than the men who swept the floors, a few cents an hour to map the heavens by hand. She was rarely allowed to choose what she studied. She was handed the plates and told to measure, not to wonder, not to theorize. And yet, in that narrow margin left to her, she found the key that would unlock the true size of the universe. She did not grow famous for it, not in her lifetime. Her discovery quietly became a tool that other, louder names would wield. In 1921, cancer took her. She was 53. She died without ever knowing how far her small, patient law would one day reach out into the dark. A few years later, a mathematician in Sweden began quietly preparing her nomination for the Nobel Prize in Physics. He wrote to Harvard for the details of her work and learned only then that she had already been gone for years. The prize is never given to the dead, and so it slipped away as quietly as she had. But her ruler outlived her, and within a few years it would be turned on the single most important smudge of light in the sky. High on a mountain in California, a new eye had opened, the great 100-inch telescope on Mount Wilson. For a time, it was the largest telescope on Earth, its enormous mirror gathering starlight out of an ocean of darkness. And a fierce argument was raging in those years about the true size of everything that exists. The faint spiral smudges scattered across the sky. What on earth were they, really? One camp said they were only small clouds of gas, drifting within our Milky Way, which was itself the entire universe. The other camp dared to whisper something far larger, that each smudge might be a separate galaxy, unthinkably far away. There was simply no way to settle it. No one could measure the distance to a nebula. The latter did not reach that far. Then a young astronomer named Edwin Hubble aimed that 100-inch giant at the great spiral in Andromeda. Night after night he photographed it, hunting for anything at all that changed. And at last, he found a single star that pulsed. A Cepheid, one of Leavitt's stars, beating quietly inside that distant blur, exactly as her law had promised it might. On one famous plate he crossed out an old note and marked that star with a single triumphant stroke. He timed its slow pulse. He read its rhythm. And Leavitt's law handed him back a distance that stopped the breath in his chest. That star was not inside our galaxy. It was not near. It lay staggeringly, impossibly far beyond the edge of the Milky Way. Andromeda was no little cloud of gas among our stars. It was another galaxy entirely, a separate island of suns. We now know its light set out on its journey around 2.5 million years ago, long before there was anyone here to look up. Sit a moment with that. 2.5 million years of travel for the light now landing softly in your eye. And Andromeda is no small thing. It holds hundreds of billions of stars, a whole second ocean of suns to rival our own. In a single stroke, the universe had grown almost past comprehension. Our galaxy was no longer everything, it was simply one island among many. And once we knew how to look, the others came flooding in, without any end in sight. Wherever the great telescopes turned, the faint smudges resolved into galaxies, grand spirals, soft ellipticals, distant swirls. Not dozens, not thousands. We now count them in the hundreds of billions, each one crowded with its own hundreds of billions of stars. The Milky Way, our whole sky, every star you have ever wished upon, all of it is just one quiet galaxy among a sea of them. It is a strange gift, to be made so small so suddenly. The cosmos did not shrink to fit us. We had to grow, slowly and painfully, to begin to fit inside it. And still the ladder kept climbing, because even Cepheids, for all their patient light, eventually fade past any seeing. Push out far enough into the deep field of distant galaxies, and their pulsing stars dissolve into an indistinct glow. To measure those far shores, we needed a candle brighter than any single star. And, remarkably, the universe had one ready. Now and then, in some distant galaxy, a dying star detonates with the light of billions of suns at once. A particular kind of these explosions, a certain doomed white dwarf, always ignites at very nearly the same true brightness. Nature had built us another standard candle, but this one could be seen almost clear across the visible universe. So the same simple trick repeated, on a far grander scale, out among galaxies too distant for any single star to be seen. Measure how bright the blast appears, weigh it against how bright it must truly be, and once again you are handed the distance. These exploding stars became the surveyors of the deep cosmos, the rung that carried the ladder past every galaxy we could resolve. In the late 1990s, two teams used them to measure the expansion of the universe, fully expecting it to be slowing. Instead, the distant supernovae came in fainter than they should have, lying farther away than anyone had dared predict. The expansion was not slowing at all. It was quietly speeding up, driven by something in the dark we still cannot name. We call it dark energy. It remains one of the deepest open questions in all of science. But notice how we found it. Not by traveling anywhere, only by patiently reading the light of distant, dying stars. There is one last rung, higher than all the rest. Beyond the farthest galaxy, beyond the farthest exploding star. Look far enough out into space, and you are looking far enough back in time to see the universe when it was very young. And there, at the very edge of the observable, a faint glow waits, one that seems to come from every direction at once. It is the afterglow of the beginning itself, the oldest light there is, set free when the young cosmos first turned clear. That light has traveled for more than 13 billion years to reach us, stretched and cooled almost to nothing on the way. We call it the cosmic microwave background. It is the final rung of the ladder, the farthest thing we will ever see. Beyond it, there is nothing left to peer into, only a wall of ancient fire, frozen forever at the horizon of time. From a finger jumping against a wall to the first light of creation, the whole ladder climbed rung by patient rung. Every step of it built by people who would never travel a single inch toward the distances they so carefully measured. And that, I think, is the quiet miracle hidden inside all of this counting. We cannot go to the stars. Our bodies are small and slow and bound to a single pale blue world. But the mind is not bound the way the body is. It can reach out to where no ship will ever carry us. With nothing but light and geometry and an almost unreasonable patience, we measured the truly unreachable. We could not cross the distance. So instead, quietly, we learned to read it. And in reading it, we came to belong to it. The universe is impossibly far, and yet, rung by rung, we have already touched its farthest edge with our understanding. With that ladder in hand, at last we could do something extraordinary. We could begin to draw a map of everything. And when the map was finally drawn, it revealed a universe far stranger and far less peaceful than we had imagined. The first thing the map showed us was motion. Nothing sits still. Our whole galaxy is falling through space at a speed that is almost impossible to feel, yet impossible to deny. Relative to the ancient light of the cosmos, the Milky Way is racing along at some 600 kilometers every second. That is more than 1,000,000 miles an hour, carrying you and everyone you have ever known silently along with it. And here is the unsettling part. We could not see what we were falling toward. Something out there is pulling an entire river of galaxies, our own included, toward a single point in the sky. We have come to call it quite plainly the Great Attractor. And for decades it hid almost entirely from view. To understand why, you have to know that our own galaxy gets in the way of our looking. The Milky Way is a flattened disk, and we are sitting inside it, looking out through its crowded lanes of stars and dust. In one whole band across our sky, that dust is so thick it simply blots out almost everything lying behind it. Astronomers call this blocked band the zone of avoidance, the part of the universe our own galaxy hides from us. And the Great Attractor sits almost exactly there, tucked behind the dust, off in the direction of the southern sky. So for years we felt its pull without ever clearly seeing its face, a gravity with no visible cause. Slowly, peering in other kinds of light that pierced the dust, we began to make out what lay hidden behind the veil. There, some hundreds of millions of light years away, sits an enormous concentration of galaxies and unseen mass. Not one galaxy, not 100. Great, crowded clusters of them, gathered into one of the densest regions we know. But the Great Attractor turned out to be only part of a far larger picture, one we did not grasp until recently. In 2014, astronomers mapped the flowing motions of thousands of galaxies around us and found something breathtaking. We live, it turns out, on the thin outer edge of a single colossal structure, a supercluster of 100,000 galaxies. They named it Laniakea, immeasurable heaven, and its every current of motion flows slowly inward, like water down a basin. And the lowest point of that basin, where all the galaxy streams are quietly draining, is the Great Attractor itself. We are a single drop, riding one of those streams, on the far pale outskirts of a structure too large to truly picture. Yet even Laniakea is not the end of the pull. Beyond the attractor lies something greater still. Farther out sits the Shapley concentration, the largest gathering of galaxies in all our corner of the cosmos. Some of our motion, it seems, is us falling ever so slowly toward that distant, immense weight of galaxies. And then, in 2017, came a stranger discovery still. We are not only being pulled, we are being pushed. Behind us, on the opposite side of the sky, lies a region emptier than almost anywhere else. A great cosmic hollow. And emptiness, in a universe ruled by gravity, effectively pushes. Full regions draw you in. Empty ones let you drift away. So we are caught between the two, shoved gently from the great void behind, drawn on toward the crowded weight ahead. A push from nothing, a pull from something, and us, threading quietly between. It is a humbling thing to learn the direction you are traveling and realize you never chose it and cannot stop. We are falling, all of us, and we have only just begun to make out the shape of the ground far below. But motion was only the first surprise. The next was the emptiness itself. When we plotted where the galaxies actually lie, we expected them to be scattered more or less evenly through space. They are not at all. The universe, on its largest scales, has a structure, and it is astonishing to behold. The galaxies are strung along vast, luminous filaments, threads of light thousands of times longer than a single galaxy. These threads cross and knot at great clusters, and stretch between them in glowing bridges across the dark. Astronomers call the whole pattern the cosmic web, and it is, quite literally, the largest structure that exists. But look between the threads, and you find the strangest feature of all. Enormous, almost perfectly empty rooms. We call them voids, vast spherical regions of near nothing, where galaxies are scarce and the dark stretches on and on. And some of these voids are so large that even seasoned astronomers struggle to hold their size in their minds. The most famous of them lies in the direction of the constellation Boötes. We call it, fittingly, the Great Nothing. The Boötes void is a bubble of emptiness some 330 million light-years across. In a region that vast, you would expect to find many thousands of galaxies. We have found only a scattered handful. One astronomer put it best. If the Milky Way sat at the center of the Boötes void, we would have thought we were alone. We would not have known other galaxies existed until well into the 20th century, so far away would they all have been. Sit with that a moment. A place so empty that its inhabitants might believe their own galaxy was the whole of creation. And the Boötes void is not alone. The cosmic web is riddled with these great hollows, some even larger, laced through everything. So the universe is mostly emptiness, immense dark rooms, bounded by thin, bright walls of galaxies, repeating on and on. Why should it be built this way? The answer reaches all the way back to the first fraction of a second of time. In that first instant, tiny random ripples were frozen into the young cosmos. Some regions a hair denser, others a hair thinner. Gravity did the rest, patiently, over billions of years. The denser places gathered galaxies, the thinner places emptied out. The whole grand web, every filament and every void, grew from those faint whispers in the newborn universe. And yet, even here, the map holds a puzzle we cannot fully answer. Some of its structures seem simply too big to be there. Our best theory says that, on the largest scales, no single structure should grow beyond a certain enormous size. But we keep stumbling on things that break that rule. Vast walls and rings and arcs of galaxies that should not exist. Each one may yet turn out to be a trick of chance, a pattern our eyes imposed on scattered points. Or it may not. For now, they sit on our maps like question marks too large to measure, quietly daring the theory to explain them. There is one more crack in our picture of the universe, and it may be the deepest of them all. It hides inside the simplest question you can ask about the cosmos. Just how fast is it actually expanding? Ever since Hubble, we have known the universe is growing, every distant galaxy drifting away from every other. And there are two clean, careful ways to measure the exact rate of that growth. Two roads to the very same number. The first road is the ladder we have just climbed together. Nearby Cepheids and exploding stars, Leavitt's method reaching out. You measure how fast nearby galaxies recede against how far away they truly are, and the expansion rate falls out. The second road starts at the very beginning, in the ancient light of the cosmic microwave background itself. From the faint pattern frozen into that first light, our theories predict exactly how fast the universe should be expanding. Two roads, one built from the nearby and the recent, one from the ancient and the far. They should arrive at the same place. They do not. The two numbers simply refuse to agree. The gap between them is not large, under 10%, but it is stubborn, and every year of better data makes it sharper. Astronomers have checked and rechecked and hunted everywhere for a hidden mistake in one road or the other. They have found none. Both methods look, by every test we can devise, to be simply, maddeningly correct. This is what we call the Hubble tension, and it is not a small technicality. It may be a crack in the foundations, because if both roads are right, then something is missing from our very picture of how the universe works. Perhaps some new form of energy in the early cosmos. Perhaps something about the dark we have not yet dreamed of. We measured the whole universe with exquisite care, and the answer came back inconsistent with itself. It is, in a strange way, a hopeful problem. The deepest cracks are often where the next great discovery gets in. For now, we do not know how fast the universe is growing. Not yet. The most basic number we could ask for, and the cosmos is still keeping part of the answer to itself. And there is one last strange mark on our maps, a single flaw in the oldest light of all. When we imaged the cosmic microwave background across the whole sky, it came out beautifully, almost perfectly smooth. Everywhere, the ancient glow sits at very nearly the same faint temperature, modeled only by the tiniest of ripples. Almost everywhere. Because in one direction, toward the constellation Eridanus, there is a patch that should not be there. It is a region noticeably, stubbornly colder than the rest, larger and deeper than our theories comfortably allow. We simply call it the cold spot. And after 20 years of study, we still argue about what it really is. The leading idea is that a truly gigantic void lies between us and that patch, chilling the light as it passes through. A hollow, perhaps 1 billion light-years across, a supervoid so large it would be a record breaker in its own right. But the measurements are not clean, and not everyone is convinced such a void is truly there at all. Others suspect the cold spot may be nothing more than a rare roll of the cosmic dice. Unlikely, but not impossible. And a very few have whispered a wilder thought, that it could be a faint bruise, left by a brush with another universe. That idea is almost certainly wrong, and it rests on the thinnest of evidence. But no one has fully closed the case. So the cold spot lingers, a cold question mark on the very first light. One more thing we can measure precisely, and still cannot explain. The map is drawn, and it is covered edge to edge in mysteries for which we have no answers yet. This, perhaps, is the quiet lesson written across the whole vast chart. The farther out we reach, the more the universe hands back not answers, but deeper and stranger questions. We climbed a ladder of pure patience to measure the unreachable, and found, at the very top, that we barely understand it. And somehow, that is not a defeat. It is an invitation to keep looking, keep measuring, keep quietly wondering. The map is far from finished, and the most beautiful blank spaces on it are the ones we have not yet learned to read. We have spoken, all this long while, of just how vast the distances truly are, and how slow the light that crosses them. And a restless thought has probably been forming somewhere at the back of your mind this whole time. If the road is too long and the light too slow, surely there is a shortcut, a back door, a hidden way to cheat the distance and step across the void without paying its terrible price. It is one of our oldest dreams, to fold the map, punch through and arrive where no honest journey could carry us. And it is worth taking that dream seriously, because clever people have spent whole careers chasing exactly that. So let us ask it plainly and answer it honestly. Are there any shortcuts hidden in the laws of the universe? Could space itself be folded or torn or slipped around to bring the far suddenly impossibly near? The honest search leads to some of the strangest ideas in all of physics, and to a wall we keep running into. Because the speed of light is not merely a speed. It is woven into the very structure of cause and effect. Break it carelessly, and you begin to travel backward through time itself. But we are getting ahead of ourselves. Let us start with the most beautiful shortcut we ever imagined. Picture the distance between two stars drawn as two small dots on a wide, flat sheet of paper. The slow way, the only way we truly have, is to crawl in a straight line all the way across the page. But what if you could fold the paper until those two distant dots were touching and simply step between them? That fold, that punched-through tunnel joining two far places, is what we have come to call a wormhole. And it is not merely science fiction. It falls quite naturally out of Einstein's own equations for gravity. As early as 1935, Einstein and a colleague found these strange bridges hiding in the mathematics. Two mouths in two distant places, joined by a throat of curved space that skips the long way entirely. On paper, it is the perfect answer. A doorway from here to there, with almost none of the distance in between. But the universe, it turns out, does not hand out doorways so easily. The trouble begins the moment you build one. A natural wormhole is catastrophically unstable. It snaps shut in an instant. The throat pinches closed in an instant, crushing whatever tried to pass, before a single ray of light got through. To hold that throat open, you would need to thread it with something truly exotic, a kind of anti-gravity matter. Matter with negative energy, stuff that pushes outward instead of pulling in, propping the tunnel open against collapse. And here is the problem. We have never found such matter existing, in any real quantity, anywhere in the cosmos. We can coax the faintest whisper of negative energy from empty space in delicate laboratory experiments, but it is a vanishing trace, unimaginably far from the mountain of it you would need to hold a tunnel open. And even if you somehow gathered it, the wormhole might still flood with radiation, or lead nowhere useful, or unravel. No one has ever seen a wormhole, not one, anywhere in the sky. They may simply be shapes that the mathematics allows, but that the real universe never actually troubles to build. A perfect road, drawn cleanly on paper, over a chasm that no one has ever found a way to truly cross. It is a strange kind of beauty, an answer flawless in every way, except that it does not seem able to exist. Still, the wormhole is not the only shortcut hidden in Einstein's equations. There is a second, even bolder idea, one that does not try to tunnel through space at all, but instead proposes, quite calmly, to move space itself. The problem with ordinary travel is that you and your ship cannot move through space faster than light, but space itself is under no such rule. Space can stretch and shrink as fast as it likes. We know this because it is happening right now, as the distant universe expands away from us faster than light. So a physicist named Miguel Alcubierre asked a genuinely daring question back in 1994. What if, instead of racing through space, you could ride a wave made of space itself? Imagine a bubble, with your ship resting quietly at its center, never moving through its local space at all. Ahead of the bubble, space is squeezed and contracted. Behind it, space is stretched and expanded. The ship simply sits in its calm pocket, while the whole bubble surfs forward on that wave of warping space. Inside, you feel nothing, no crushing acceleration, and the far star is carried toward you faster than any beam of light. It is the warp drive, made almost respectable, a real solution written in the honest language of physics. For a moment, in the 1990s, it seemed the door to the stars had been quietly cracked open. But then people began to add up the bill, and the numbers that came back were staggering beyond all reason. To warp space that way, you again need that exotic negative energy, and, at first, almost unthinkable amounts of it. The earliest estimates demanded more mass energy than exists in the entire visible universe, just to move one ship. Later, cleverer versions trimmed that down enormously, from the absurd all the way to the merely hopelessly impossible. Some recent work even sketches gentler warp bubbles that need no negative energy at all, a genuinely hopeful surprise. But every one of those gentler versions still demands the mass of a giant planet, and still cannot exceed light. And lurking beneath all of it is a deeper, more troubling problem than any mere shortage of energy. Because a true faster-than-light drive would not only carry you across space, it would carry you across time. Chain two such trips together, in just the right way, and you could arrive back home before you had ever left. You could meet yourself, warn yourself not to go. That is not a technical hurdle, it is a paradox, the kind the universe seems to guard against with real determination. Again and again, whenever we sketch a true shortcut, this same shadow falls across it. Broken cause and broken effect. It is almost as if the cosmos has quietly decided that some doors must stay shut, no matter how cleverly we knock. The warp drive, like the wormhole, remains a gorgeous equation, waiting on an exotic ingredient we have never once held. There is one more place people go looking for a loophole, down in the strange, small world of the quantum. Two particles can be linked or entangled in a way that Einstein himself uneasily called spooky action at a distance. Measure one, and the other responds instantly, or so it seems, no matter how vast the gulf between them. Surely the hopeful thought runs, that instant link is a channel, a way to send a signal across the galaxy at once. It is a seductive idea, and sadly it simply does not work. The result you read from your particle is purely, perfectly random. You cannot choose it or shape it into a message. Only afterward, comparing notes by an ordinary, slower-than-light signal, do the two of you ever see the hidden pattern. The connection is utterly real, but it carries no information you can use and no thing that you could ever ride. Physicists have proven this carefully. It is called, quite plainly, the no communication theorem. The loophole is sealed. And it is the same story with every other trick the universe seems, at first glance, to offer for outrunning light. Yes, the space between distant galaxies stretches faster than light, but it carries no ship, no signal, only emptiness. Sweep a bright point of light across the distant face of the moon, and that dot can race across it faster than light. But that dot is not a thing. It carries nothing. No matter and no message ever actually makes that crossing. Over and over, the same quiet lesson. The appearances tease us with speed. The reality closes every single door. Nothing that carries information, nothing that carries cargo, nothing that carries you has ever beaten the speed of light. Not once. Not anywhere. Not in any experiment we have ever devised across more than a century of trying to. The particles that make you, the light in your eyes, the signals crossing your mind, all of them obey that one limit. It is, as far as we can honestly tell, not a rule that is waiting to be broken. It is simply how the universe is built. So let us give the honest verdict on the shortcut, the one the dream has been quietly waiting for all along. As far as we truly know, and we have looked very, very hard, there is no back door out of the distance. Every shortcut we have ever imagined runs headlong into the same three walls, again and again and again. Exotic matter we cannot find, energies we cannot gather, paradoxes the cosmos forbids. The wormhole needs the impossible to hold it open. The warp drive needs the impossible to push it along. And the quantum link, for all its spookiness, refuses to carry so much as a single whispered word. The speed of light is not a speed bump on the road to the stars. It appears to be the shape of the road itself. It is not that we are not yet clever enough. The universe seems genuinely built this way, from the ground up. And there is a strange dignity in accepting that, rather than pretending a miracle is always just one more year away. The distances are real. The limit is real. And no amount of wishing has ever moved a single star an inch closer. This is the hardest answer in our whole long story, the one the dreaming has always, quietly, refused to hear. No shortcut, no fold in the map, no door. The far stays far. And yet, and I do mean this, the dreaming was never wasted. It almost never is when we dream this carefully. For in chasing the impossible shortcut, we mapped the exact shape of the possible in astonishing, lasting detail. We learned with breathtaking precision what the universe forbids, and so by that, what it quietly allows. Every closed door taught us something true about the room we are actually in. That is not failure. That is knowledge. So no, we cannot cheat the distance. But in learning that we cannot, we came to understand the distance itself. And there is one honest question left before we let this dream of going far finally lie down and rest. We asked what one lifetime could do. The answer was humbling and small. But we are not the end of the story. We may be only its very early pages, its first uncertain paragraph. What could a civilization do, not in one brief life, but across 1,000,000 patient years of deep, unbroken time? If there is no shortcut through space, then perhaps the only road left to us is a long, slow road through time. So let us set aside the single lifetime and the single ship and ask the question on a far grander scale. Not what can you do, or I, but what could a whole civilization do, given oceans of time we can barely imagine? Because there is one resource we have been quietly ignoring, and it changes everything. Patience. Deep, deep patience. The stars are slow, yes, but a civilization need not be in any hurry, the way a single mortal always is. Even without any shortcut, even bound forever below the speed of light, the galaxy is not truly beyond reach. Send slow ships to the nearest stars, let them settle, and send their own. Each step is small, and each crossing takes centuries. But the steps do not have to stop. They simply continue. Star by star, world by world, a patient civilization could ripple outward across the whole of the Milky Way. And the mathematics of it is genuinely staggering. Even at a modest crawl, the wave need not take so very long. A few million years, perhaps. An eye blink for a galaxy. The galaxy is 100,000 light years across, and yet it could, in principle, be crossed and filled. Not by us, but perhaps by something that still remembers us, our distant, patient, deep-time descendants. And such a civilization would not merely travel between the stars. It would learn in time to use them. Think of how much light a single star pours uselessly into empty space, every second, for billions of years. Nearly all of it streams away into the dark, forever wasted. Long ago, a physicist named Freeman Dyson imagined catching it, all of it, with a vast swarm of collectors. Not a solid shell, but a great cloud of countless panels, encircling a star to drink its entire output of light. A structure like that could power a civilization beyond anything we can presently even find the words for. Physicists sketched a ladder for this, a way to rank a civilization by the sheer energy it can command. One that masters all the energy of its home planet, then all the energy of its star, then of its whole galaxy. By that measure, we are not even at the first rung yet, a small thing, warming its hands at a fire it barely taps. But nothing in the laws of physics forbids the climb. Only time and will and enormous patience stand in the way. A civilization that harnessed a whole star could do things that would seem, to us, entirely indistinguishable from magic. It might even, some have dreamed, learn to move a star itself, to steer it, slowly, across the face of the galaxy. Nudged along by its own captured light, over hundreds of thousands of years, a star could be sailed to a new home. Imagine that. Not traveling to the stars at all, but bringing your star with you on a journey of long ages. It sounds like pure fantasy. And yet every piece of it obeys the ordinary, honest physics we already understand. This is what deep time and patience could buy. Not a shortcut, but a slow, patient mastery of the whole neighborhood. And yet, even here, at the very summit of everything we can imagine, the old wall is still quietly waiting. That same dark energy does not pause to admire our ambitions. As the long eons pass, the distant galaxies keep fleeing, faster and faster, over the horizon of the reachable. Even a civilization that filled its entire galaxy would find the others slipping, one by one, forever out of reach. In a few billion years, our own Milky Way will collide and slowly merge with the great spiral of Andromeda. The two will become one vast new galaxy, and our small local family of galaxies will gradually draw in close. But beyond that bound little island, everything else will have fled beyond any crossing, any signal, any sight. A civilization in that far future would look out and see almost nothing. One galaxy, alone in an empty dark. They might never even guess that a wider universe had ever existed, its evidence long since carried away. So even the grandest reach we can possibly dream of runs, in the end, into the same gentle, absolute limit. The reachable universe only ever shrinks. It never grows. Deep time may offer a whole galaxy, perhaps, but it can never, ever offer the whole of the universe. So there it is, the fullest, most honest answer we can give, stretched all the way to the very end of ambition. Far, yes, perhaps a single star tamed. Perhaps across ages, a whole galaxy crossed and quietly made home. Never everything, never everywhere, always bounded in the end. The universe is generous. It offers more than any single life could ever hope to hold, or even to see. And it is strict. It keeps its farthest shores forever beyond us, no matter how patiently we reach for them. Which brings us, at last, all the long way back home, and to the quiet truth this whole journey has been circling. So, we began, a long while ago now, with a single, simple question. Just how far can we actually go? And we have followed that question outward, patiently, all the way to the very edge of what exists. Let us be honest, then, about the answer our bodies give. On our own, we cannot go very far at all. A handful of us once walked on the moon. Our machines have slipped past the outer planets and brushed the sun. Given centuries and enormous patience, we might cross to the nearest stars and settle a few quiet worlds nearby. But the galaxy is 100,000 light-years wide, and it is only one island among uncounted billions. And the universe is not waiting politely for us. It is expanding, faster and faster, carrying the far galaxies away. Every day, quietly, more of the cosmos slips beyond the horizon of anything we could ever hope to reach. The vast majority of the galaxies we can see are already gone, in this sense, forever beyond any journey. So if the question is whether we, in these fragile bodies, can travel the universe, the honest answer is no. We are held, gently but absolutely, by the size and speed of it all. And yet, that is nowhere near the whole of the story, because there is more than one way to go far. We could not sail to the stars. So instead, we learned to reach them with light and patience and thought. We could not cross the gulf to a single star, so we measured its distance from the faint shift of its place. We could not visit a far galaxy, so we read its remoteness in the slow, steady pulse of one burning star. We built a ladder out of pure ingenuity, rung upon rung, and we climbed it with our minds alone. From a jumping finger to a pulsing star to an exploding sun to the very first light of all creation. And with that ladder, we did something no ship will ever do. We touched the edge of the observable universe. We mapped the great web of galaxies, its bright, shining walls, and its immense dark rooms of nothing. We traced the currents we are caught in, and named the vast, unseen weights that pull us through the dark. We looked back nearly 14 billion years to the faint afterglow of the beginning itself. We did all of that without ever leaving home. The most far-reaching journeys our species has ever made were made sitting still, looking up, and thinking carefully. A telescope, a photographic plate, a page of patient arithmetic, these carried us where no rocket ever could. The body stayed on its small blue world, but understanding went all the way out to the horizon of everything. That, perhaps, is the real answer to how far we can go. In body, not far. In understanding, almost unimaginably far. We are the part of the universe that has slowly, patiently, learned to comprehend the whole of itself. And there is something quietly staggering in that so small a creature could hold so vast a thing in mind. Because we are brief, and we are small. There is no gentle way around that, and no real need to hide from it. A human life is a flicker against the long ages of the stars we have been speaking of all this while. The sun will burn for billions of years more. The last red stars will glow for trillions after it is gone. And the true deep dark that follows, the long, quiet end of everything, stretches almost beyond thought. We live in the bright, brief morning of the cosmos, and we will not see the smallest fraction of its story. Even time itself, we learned, bends around us, running slow for the fast traveler, stretching near the speed of light. A Voyager riding close to light could cross the galaxy in one lifetime, and return to an Earth long since gone. The distances of space and the distances of time both fold and stretch in ways our small lives were never built to feel. And still, we worked them out. We wrote down the true shape of space and time and checked it against the sky. The body is bound to its moment and its small, warm place. But the mind slips those bindings, quietly, again and again. It reaches back to the first light and forward to the last, out to the far edge and down to the smallest instant. We cannot go there, but we can know it. And knowing, it turns out, is its own quiet kind of traveling. Perhaps that is enough. Perhaps it was always meant to be the small place where the universe wakes up and takes its own measure and wonders at what it finds. And what it finds at the very limit is not a neat and finished answer. It is a horizon full of open questions. We do not know what most of the universe is even made of. The dark that shapes it stays nameless still. We do not know exactly how fast it is growing. Our two best answers still stubbornly disagree. We cannot see what is pulling us across the dark, nor say why one patch of the first light runs cold. We measured the unreachable with exquisite care and found, at the top of the ladder, that we barely understand it. And here is the strange, quiet grace of that. The unanswered questions are not a failure. They are the invitation. They are the reason there will always be a next night and a next question, and someone patient enough to ask it. Every answer we have ever won was once exactly this: a mystery sitting at the edge of the known, waiting. So the not knowing is not the end of the journey. It is, in truth, the very thing that keeps the journey going. We reached as far as we could reach, and the reward for reaching was a farther, stranger shore to wonder at. That is not a disappointment. I have come to think it is the most hopeful thing about us, that we are still, after everything, a species that looks up at what it cannot reach and quietly tries anyway. Which brings us, gently, back down, back from the edge of the universe to wherever you happen to be right now. It is late. That is usually when these questions come, in the quiet, once the day has finally let go of us. And I hope tonight, the sheer size of it all feels less like a weight and a little more like a comfort. Because you do not have to carry any of this. The universe is not asking you to cross it or to solve it. It is only asking, if you like, to be looked at now and then, with a little wonder before you sleep. You are small and brief and made, every atom of you, from the dust of stars that died before the sun. The same patient curiosity that measured those distant stars is in you, right now, quietly. It always has been. You are the universe, grown local and warm and awake for a little while, wondering how far it can go. And the answer, tonight, does not have to be anything at all. There is nowhere you need to reach before morning. The far galaxies will keep drifting outward whether you watch them or not. They do not need your worry. Let them go for now. Let the vast, slow, patient cosmos simply be vast and slow and patient around you. The stars have kept their long silence for billions of years. They will keep it gently through this one night. So set the questions down just for now. They will still be here, faithful and unhurried, whenever you return. There is no distance you must cross tonight. Only rest and the soft, ordinary miracle of being here to wonder at all. Well, this has been a long way to travel together, and I am very glad you came along for it. Space, slowly, for the hours you cannot sleep. That is all this ever really needed to be. Close your eyes now, if you like. The universe will hold its place until you wake. It is impossibly far, and you are exactly where you need to be. Rest easy. Sleep well. Good night.